よろしくお願いします。Hello everyone, welcome to my short talk titled Overcoming Callback Hell when Integrating C into Rust. Today I'll be sharing a little bit about my experience writing a Rust wrapper for the NVIDIA DOCA library, which is a C library, and hopefully the title gives you a little bit of a hint as to some of the problems I faced when writing this Rust wrapper. So first, let me do a brief self-introduction. My name is David. I come from the University of British Columbia in Vancouver, Canada, and I'm an undergraduate student there studying computer science. And so far, two of my main interests have been computer systems and programming languages. I've found computer systems to be interesting because I like understanding our computer systems from a fundamental level before being able to look at them as an abstract concept and higher levels. So I like getting into the details of stuff. And I like programming languages because in a field where we're very technical and logical most of the time, I think programming languages is a great chance to be creative and express your individuality, which is why one of the things I'm enjoying is writing my own programming language. And actually, before this year, I've mostly been programming in C, C++. So I'm actually fairly new to Rust. I only started this year. So hopefully that means I can offer a fresh perspective to you all. And hopefully, if I make any mistakes, I can learn something as well. Okay, before we get into the Rust part, let's first talk about why anyone would choose to use C or FFI in the first place, especially in our modern world where we have Rust, memory safe language with a lot of language features, where C, it barely have a standard library and it's really simple, right? So first, let's take a look at what kind of programs are written in C to try to understand. So we have the three major operating system kernels, as well as some other types of systems that are close to hardware, such as embedded systems, right? And we also have some software libraries, which are quite fundamental to most of our software programs. And if you take a look at the software libraries, what they have in common with the OS kernel and embedded systems is they are very math heavy. So they're going to have to target specific platforms in order to make the best use out of the hardware resources. So all of these kind of systems that are very close to hardware are going to be very platform dependent. And C, having existed a long time, is going to be very portable. And it's also very simple to write. And not only is it simple to write, it's also simple to write a compiler for because the language is so simple, right? So that might be why there's so many implementations and different backends available. And so this flexibility really, I think, is why C is used so much even to this day. So then what does Rust give us, right? So Rust programs give us memory safety by proof. Basically, we're following borrowing rules. So the borrow checker was kind of the selling point of Rust for me when I got into the language. And by following these rules, our programs are made memory safe by proof, right? But just because we follow these borrowing rules and we made our program safe doesn't mean if our programs were safe, we had to have borrowing rules in the first place. So it's not if and only if, right? So this extra time spent checking is great because we get memory safety, but at the same time, it's time we could have spent designing our system, testing it, validating it, and going through regulatory processes, things like that, engineering processes where we all need to make our programs work at the end of the day, right? On top of learning the language, I think, coming into the language, it took a while to learn. And yeah, at the end of the day, developers, we're just trying to write robust and usable software at the end of the day that's useful, right? So hopefully, although these two languages are very different, let's try to consolidate them. Okay, so personally, my motivation for writing a Rust program, which is using a C library, was I had some application written mostly in Rust. It was using a bunch of Rust libraries in the first place. But I wanted to use this Doca C library, which was only available in C, right? And because it was already written mostly in Rust, this new C library is the foreigner here. I kind of wanted to integrate into my framework. And in order to take advantage of Rust memory safety and language features, I need some kind of interface between Rust and Doca, which is a C library, right? Okay, so now let's talk about what Doca actually is. So Doca is a collection of software libraries from NVIDIA made for their Bluefield line of data processing units. And it's totally okay if you don't know what a data processing unit is. It's a relatively new piece of hardware, which was created as kind of an upgraded version of your traditional NIC. So the thinking was, we have servers which perform network tasks because they have to talk to clients and other servers quite a bit. And it's doing these repetitive tasks all the time that's consuming our host CPU resources. But we already have a card, a NIC, that's doing some very basic packet processing, right? So why not just add some more features to do those repetitive network tasks on this new hardware card as well? So usually it contains hardware accelerators as well as some degree of general purpose compute. And yeah, so moving your application onto this new card, this process is called offloading. And this is kind of what I wanted to do with my Rust application. Okay, so Doca uses an event-driven programming model, which basically means we have a task which represents a unit of work that we want Doca to do. So maybe it contains some data that we want to give to Doca, and Doca is going to process that through its hardware and give it back to the user. And that task is going to be submitted through something called a context. A context is basically just some kind of handle or interface for one kind of Doca function or library. And then the whole thing is going to be put together by this progress engine, which is basically the event engine for Doca. So the event engine is going to manage these tasks and actually run them to completion. So, oh yeah, and also just to note, because we're using C, we also have to manually manage our resources, right? And as we'll see, as we get into the problem, it uses callbacks to handle these events. And these callbacks will involve things like void pointers. So basically, you're casting the type away from your data. And yeah, we'll see how that's a problem. Okay, so the first step for using Doca is basically to set it up, to attach the progress engine to the context as well as register your callbacks. And this is some simple code of what that might look like. So first we're creating it just through some Doca API calls. And then we're going to set it up by attaching the progress engine as well as registering our callbacks. And our callbacks are just function pointers. This is how they exist in C, so they can be defined elsewhere. And then once you have everything set up, you want to create your task. So you want Doca to do some work. So you can submit that to the context. And then after you've submitted it, you want to check until it's done, right? You want the result of the task, hopefully sooner rather than later. So this is what that might look like. So here's us creating our progress engine and setting everything up. And here we're calling this new function now compress, which is actually handling the task creation submission. And then we're just going to keep polling until we finally arrive at our callback. And when we finally do arrive at our callback, when our task is complete, our task, which was a Doca object, remember, is now going to be transferred back into the user space. And because it's now in the user space, we're in control of the task in ownership. So we're going to have to free that task when we're done because this is C. So here's just a simple example of what a callback might look like. So we're basically just doing something with the result and then freeing the task. Okay, so what if you wanted to have a follow-up task? So usually your program is going to do more than just one thing, right? For our example, let's say we wanted to do compression a second time with a different set of data, maybe. Oh yeah, I think I forgot to mention earlier, but compression is just an example of a context. And for example, there's also a hashing library with a context. But yeah, for now we're going to stick to compress as the example. Okay, so same thing as the first task, you're going to want to pull the progress engine to progress your task. Okay, so this is what it might look like when we're actually coding it up. So now instead of just stopping the context, ending our program once we're done with the first task, let's call the compress function we saw earlier again for the second task. And it's going to do the same thing. It's going to create the task, submit it, and we're going to pull it again. And then we're going to end up back in this context, right? I mean, sorry, back in this callback. So here we kind of start to see the problem. So our program logic is being shifted all into our callback, right? And because we're being forced to write our application logic there, it's going to be tangled in with the FFI logic, which if we were just writing C would be fine, but since we want to write Rust, we want to write Rust, we want to write safe code. This is kind of mixing it up with the FFI stuff, and it's going to make it very hard to generalize for more than one use case, right? Okay, so in practice, you're probably going to have more than one kind of context you want to use. You have more than one kind of callback for each different task in case you want to do something different for the results. And yeah, so basically, it's going to get more and more complicated. That was just a simple example, and I think it was already quite complicated, at least more than it needed to be. And just a side note, because you have this non-trivial mutual recursion going on, you're eventually going to run into some problems with things like the locks and the stack, especially for locks, because I think at any time you want to use multi-threading, you're going to have to deal with, well, first of all, you're going to have to use a reentrant lock for sure. And you're probably going to have a deadlock somewhere if your program is non-trivial. Okay, so what can we do about this then? Well, we want to somehow pull our logic away from the callback and back into our application zone, right? So, we also want to somehow manage our DOCA objects through some kind of RAII, or somehow no longer have to manually manage, because that will be prone to things like memory leaks and use after free, right? So we want some kind of intermediate interface between our Rust application and the DOCA and FFI code. Okay, so the solution I came up with was pretty simple. Basically, I just had some kind of wrapper structure object, and this wrapper structure is going to provide some kind of interface for your Rust application. And the wrapper is going to take care of interacting with both DOCA directly as well as your callback. And the important thing here is we have some way to store the result from the task inside the wrapper. That way, as we'll see in the following slides, the callback can just take care of creating that result, putting it in the wrapper, then we can return from the callback and continue in our Rust application. Okay, so this is a similar diagram from earlier, but now for our modified application with the Rust wrapper. So basically what we're able to do is we're able to decouple the callback logic, which is responsible for interacting with DOCA, progressing the event engine, away from our actual application code, which is focusing on what we actually want to get done. Okay, so let's take a look at what an implementation for just the wrapper structure would look like. So here again, I have a wrapper for the compress context. And first, you'll notice that the progress engine is a member. And I chose this design because the progress engine, when we pull it, it's eventually going to call the callback for our task. And because we want to put that task inside our wrapper, it's going to modify our wrapper, right? So we actually need a mutable borrow to our compress context. So if you made those two separately and you were using pointers underneath, Rust would have no way to know, right? So this is just one way we're manually enforcing our Rust safety rules. And of course, we have the result map, some way to store the results. Okay, so one thing we need to do differently for step one, which was setting everything up. And what I didn't mention earlier is when you are registering the callbacks, you usually have something that you can also pass along with the callbacks, some extra data. to help you give some context outside the callback, because they're basically jumping in from somewhere else in your code, right? So this extra data comes in the form of a void pointer, and we're just going to set it as a pointer to our wrapper object. So this is what the new code for initialization might look like. Yeah, so here we're casting a pointer of our context into a void pointer, and this is like definitely not safe for us, right? But that's why we had the progress engine as a member earlier to help us enforce the borrowing rules. We're doing that manually. And there's another thing to remember, which is when you're using pointers for callbacks and your pointer you won't be able to change your pointer, you want to make sure that the pointed to object, which is our context, its memory address has to stay constant, right? So one way we can do that is use pin box. And you could either do that by making like the creation function for the context, return a pin box, or you could have some kind of opaque data structure where the only member is a pin box or something like that. And unlike earlier, when we're giving our function pointers for callbacks, there's something we can do, which is pass self as a generic parameter. And we'll see in a few slides why that's a little safer than just passing the raw function pointers as we would do in C. Okay, so now, now the application is being pulled again and our callback is being run. But unlike the C version, now all the callback is going to do is access the wrapper through the pointer and place the result in there somehow. And to do that, I defined some kind of interface for the callback to interact with the context. And first what we have is just some kind of way to represent the different kind of events. And here we have, as an example, the state change, which is basically just when your context gets going, you'll get a state change notification. But as we saw earlier, we also have the compression task. And I also put in decompress here just as an example. And we have some kind of trait to define the interface where the callback can send the event to the context, which is just a very simple, just one function where we have an event as the parameter, right? And yeah, that's just where we call it from the callback. So yeah. And as I mentioned earlier, we have the self as an extra generic parameter to the callback. And by using a trait bound for the generic for each callback, we're kind of making sure that the pointer given to this callback is going to be interfaceable with the context. And by using the self keyword, even if you copy paste that code, it's going to be the same for every different context, right? Okay, here's a little more advanced of an example for the compression complete callback. Here again, we're sending the event. And you'll notice that this is actually a macro. And if you look carefully earlier, actually you have two callbacks for each event completion. You have the successful case and the error case. And those are going to be very similar. So if you have a situation like that, you can write a macro to generalize the parts that need to be generalized, because most of it stays the same, right? All we're really changing is what kind of result is being sent to the context. Task now becomes an internal implementation detail because it's only managed underneath the wrapper and the user doesn't need to interact with it anymore, right? But we might have some kind of object where we do need the user to interact with that's also interacting with DOCA. And for something like that, such as the buffer that we want to write and read from for the compression, we can have some kind of view object where we let the user interact with it, but we manage the lifetime through the context. But there are other ways to do this, I think. Okay, and finally, after you're done polling, you want the result. And to do that, we go back to application land, and we can access the wrapper through the wrapper's API. And all put together, this is kind of what it's going to look like. So they have the same creation functions as before, but now they're member functions and they're giving you a wrapper back. But the underlying code is going to stay the same. And for the task submission, now that the task is hidden under the wrapper layer, we just have some kind of API for the kind of task you want to do, right? So here we're doing compression. So naturally, we want to compress some data. And also similar to earlier, we just keep polling, but because now we separated the polling from actually handling the result, after polling, we can check to see if there's a result. And then when we finally do get a result, we can do something with it. And at the end here, I'm also, because I have the buffer pair as a managed by the context, I'll also return that back to the context. Okay, so let's summarize what we kind of did. So what we did was actually kind of simple, right? There's nothing super complicated going on. We wanted to offload part of our application to use Doca, which is a C library. We figured out that Doca uses a callback-based event engine, which forces our application logic to be inside these callbacks. And we realized that was kind of an issue, so we wanted to pull our logic out of those callbacks and back into our application. So we created a wrapper object to act as an intermediate interface. And the last point I want to say is also, there are a lot of Rust features that help us keep our code a little safer than if we were just writing raw C code, right? So we use pinbox, we use generics, we use the self keyword, just little things that help us build a safer program. And just a few takeaways for this presentation. I think don't be afraid of writing FFI or Rust, unsafe Rust. Even Rust itself is, the standard library is written on top of a lot of unsafe code, right? So you kind of need some kind of unsafe foundation in order to write in safe Rust. And also, we talked a little bit at the beginning about why anyone would use C. And this whole process overall took us a lot more effort than if we were to just write it in C, right? So whether you pay through performance, which we kind of do through a wrapper, or through time spent coding, you're going to end up paying for the, you're going to have to pay for the abstraction somehow. And lastly, just try to be creative and work around all kinds of constraints and APIs. Not all software is going to be written the way you want it to be. At first, I kind of wanted a perfect solution, but that was kind of impossible. So eventually, I had to compromise, think about what could work, and think about what compromises were worth the compatibility and safety. Okay, thank you very much for listening. Yeah, let me know if you have any questions. Thank you.
デイビッドさん、ありがとうございました。これから質疑応答に移ります。
Thank you for informative presentation. One question is coming. So, do you think a future where Doca interfaces are provided in Rust is possible? Maybe that using future instead of using the Doca's interfaces or your own systems?
That's hard to say, but in my opinion, I think NVIDIA is quite proprietary, and even the C API is proprietary. You only have the headers. So I don't think NVIDIA themselves would do it, but I do hope someone, if hopefully Doca becomes more popular as DPUs do as well, someone would write a Rust wrapper that has more support.
Yeah, thank you. That's it. Okay, next question. Here. It's very impressive abstraction. How much overhead does your abstraction introduce? Overhead, regarding the overhead.
That's a good question. I did try doing some benchmarks on it, but the latency for the Doca tasks are actually quite low because they're very close to hardware. They're on the order of microseconds. So even just timing, the overhead of timing it was quite a bit compared to the overhead of just doing the task. So I think I would have to do more to know for sure, but yeah, I don't have a exact figure at the moment. But I remember one thing I did was for the result map, at first I was just using the standard Rust hash map, but then I realized that the Rust hash map uses a fairly slow hashing function. So I switched to like I think the library is called int map or something. Basically, it takes the integer directly as the hash, and that didn't seem to affect the performance. So hopefully not too bad, but yeah, I don't have an exact number.
Cool, thank you. Maybe this would be the last question. How did you get the rough idea? Were there some examples on the internet or not? How did you get your wrapper's idea?
Oh, good question. I was just doing a little research and I encountered on another wrapper for Doca, but it was quite old and very limited. It didn't support much. So it didn't fit my needs, so I just decided to write my own in that case. Yeah.
Thank you. That's all from our side.
じゃあ、ありがとうございました。最後にもう一度拍手をお願いします。